Hello and welcome to our webinar, Connected Vehicle System Design for Signalized Arterials. My name is Brendan Williams. I am the Research Program Administrator at Portland State University's Transportation Research and Education Center. TREC leads the National Institute for Transportation and Communities, one of 7 national university transportation centers funded by the U.S. Department of Transportation. NITC's research priority is improving mobility of people and goods to build strong communities. NITC consortium members are the University of Utah, University of Oregon, University of Arizona, University of Texas at Arlington, and Oregon Institute of Technology. We enjoy connecting our researchers to you, our audience. During this webinar, if we have any problems, please bear with us for a few moments. Our presenter today is Dr. Yang. He is an assistant professor in transportation engineering in the Department of Civil and Environmental Engineering at the University of Utah. His current research areas include evacuation planning and operation, traffic operations with connected automated vehicles, intelligent transportation system, traffic safety, network flow modeling, and unconventional intersection design. Our upcoming NITC events, this Friday, May 15th, starting at 11:30 a.m. Pacific time, we'll have a Friday transportation seminar presented by Matt Kelly from the Portland Bureau of Transportation. Safe Speeds Save Lives, how Portland is managing speeds for safety. Our next NITC webinar is next week on May 19th at 10 a.m. Pacific time. Natural pozzolans in the Pacific Northwest and their beneficial uses, presented by Dr. Matthew Sleep from the Oregon Institute of Technology. A brief overview. The presentation by Terry will be about 40 minutes long. Then we'll have 15 minutes to answer audience questions. During the presentation, please submit your questions via the GoToWebinar control panel with the questions section. After the webinar, you will receive an email with a link to the video recording and presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. Instructions on how to redeem the credit will be included in your post-webinar email. All right, I'm gonna turn this over to Terry.
All right, thanks a lot for the introduction, Brandon. Good morning, everyone. Sorry, I should say good afternoon for those folks from the Eastern Coast. My name is Terry Yang. I'm assistant professor from the University of Utah. And today I can present some of our research work that related to the connected vehicle system design for signalized arterials and in sections for sure. Firstly, let's take a look at the outline here. I would like to give you a brief introduction about the research background here, and along with the connected vehicle system architecture we proposed, and then along with some function related to data collection, dynamic signal control, smart traffic signal control at intersections, and also I want to highlight some additional discussion issues related to the connected automated vehicles. All right, so in terms of the background, firstly, let's take a look at the connected vehicles, for short is CV. With different communication technology such as DSRC, C-V2X, 5G, DMB, so on and so forth, the CV technology can allow the vehicles to communicate and exchange information between vehicles and also infrastructures. And nowadays there's a bunch of V2X communication channels include V2V, vehicle-to-vehicle communication, V2I, vehicle-to-infrastructure, vehicle-to-pedestrian, so on and so forth. So the connected vehicle is definitely not a new concept, and but it's a very popular concept since back to maybe 7 to 8 years ago. And nowadays, there's a lot of CV application and CV related to infrastructure has been installed across the US. And on the other track, automated vehicle, AV, or autonomous vehicle, and also received a lot of attention in these years. And the SAE defined the 5 levels of vehicle automation here. So usually starting from level 3, the AV requires the assistance of automated driving system (ADS) to control the vehicle trajectories. And in most of the time, we call the level 1. We call the level 2 to level 3 as the automated vehicle, and we call the level 4 and level 5 as the autonomous vehicles. So there's definitely a different definition of automated vehicle and autonomous vehicle in terms of different level of vehicle automations. But even though with a lot of implementation of either CV or AV in practice, and we have seen a lot of benefit in safety improvement or mobility improvement, but nowadays people have seen the limitation of the either CV or AV on the street. So for example, for the CV, we can definitely gather information from the connected vehicles in real time, and we can also send back the information back to the CV. But since there's no vehicle automation on board, CV still rely on the human drivers. So in that case, you can definitely send some notification or message to the driver, but there are some people, they really criticize this function because they feel like if you are sending message to the driver, it may distract the driver and cause some traffic accident. So but on the other hand, if we don't send message back to the CV, and the CV literally becomes a real-time proper vehicle on the road, and then we lost a lot of benefits from the CV technology. And for the AV, basically use the onboard sensors to detect the object and to understand the driving environment, and then to activate the ADS. But in that case, you can imagine the AV still using the reactive control, because you have to detect something, then give the response. You cannot do the proactive or planning control. So with those limitations, nowadays more and more people start to look at the combination of the CV and AV technology, and that becomes what they call connected automated vehicle, CAV. So with the CAV technology, the connectivity can allow the exchange of traffic information between the vehicles and infrastructures, and the ADS, the automated driving system on board, can control the vehicle trajectory based on the real-time data from onboard sensors and also the CV communication channels. Okay, a typical case is when you have a AV get approached to an intersection, and if you don't have the connected vehicle technology on board, you're going to use a camera to look at the traffic signal light, and then you give the responsive control. And as many of you know, we always have the dilemma zone issues at the intersections. So in that case, even though you're using AV, you cannot prevent dilemma zone issues. But if we have the CV technology on board, we can receive the SPAD information, signal phasing and timing plan ahead. Then we can do the earlier planning of the trajectory. Then we can prevent the dilemma zone issues, right? Okay, so in terms of the CV system architecture, this is what we propose here. For the control level, we have 3 different levels of controls: a corridor level, intersection level and vehicle level. Even though we may see some research that has been done on the network level, but in practice, I would say the corridor level would be the most efficient one. And so with different control levels, here we have different modules that in a CV-based traffic signal control system. So the module 1 is the communication and data collection functions. So we're using different technology to collect the real-time information from the connected automated vehicles. And then we can have the corridor level intersection coordinations. And then module 3, smart traffic signal control at intersection level. And then we can also promote some multi-modal traffic signal control system. For example, we can promote the transit signal priority control at the intersections. And the Utah Department of Transportation, they actually implement the TSP, the transit signal priority control in Salt Lake City, and the system has been fully functioning since 2017. And in this webinar, we're gonna focus on the module 1 to module 3, and because we don't have enough time to go over the knowledge related to the module 4. So for the data collection, at present, there are 2 very different technologies that can be used to support the V2X communications. So the first one is the DSRC. So DSRC stands for Dedicated Short-Range Communications. So it is often used for direct communication in a local environment, and it has been widely implemented in the US since 2017. And as far based on my knowledge, I think many states across the country has implement the DSRC-based infrastructure, the roadside unit, to support the operation of connected vehicles. And I also remember back to 2 or 3 years ago, and US DOT is considering to set up the DSRC as a standard for supporting CV communications, but that plan has been canceled later on because of the new technology, the more recent one, which is called CV2X. So the CV2X utilizes the cellular technology to provide a link between the vehicle and the rest of the world, including the other vehicles and other traffic signal control, infrastructures. And this, these 2 technologies are actually addressing the identical use cases and having identical network, security, and application layers. And they're even using the very similar spectrum band. So we can definitely see a lot the computation between these 2 technologies. And with this computation, we can also observe the engineer dilemma. So in the midst of the platform war, engineers must choose which platform to commit their development time and cost to. And I think some of you may already know the DSRC are not compatible with the CV2X on the street because they're using the same communication channel. And starting from last year, UDOT invest about $60 million to establish the connected vehicle communication network in Salt Lake City. And I had a conversation with them back to this February, and they told me, and they are, because they don't know which one will becomes the standard in the future, and then they have no choice but to install both DSRC and CV2X infrastructures in Salt Lake City, and side by side. But the issue here is if you turn on the DSRC, you must turn off the CV2X because they are competing for the communication channels. So some company comes out some potential solutions is to combine the DSRC with a CV2X. So I remember there's a company called Auto Talks. So they're a provider of the V2X chipset. So they have developed some technology to unify the DSRC and CV2X in a single solution, as within a single package. But I don't see any application or implementation of their product yet. So we are still seeing the engineer's dilemma in picking one of these technology to support the V2X communications. And there's also some other challenges from the data collection and communication aspect. So as we know, the communication is based on the network. So that would be similar to our transportation network. So when you imagine there are all of the vehicles on the street are CV or CAVs, so then we have a lot of communication need, and that can cause a communication jam or communication congestion on the network. So in that case, we may need to consider to provide some communication priorities to the CAVs, because the CAV has to rely on the data to control the trajectory. And in terms of the CV, because the vehicle still relies on the human drivers, so we can give a lower priority to them. And in that case, we can potentially solve the communication jam or communication congestion problems. So we have another colleague on this project that talks about these issues. And if you would be interested on this to look at this challenge, please look at our project report that's submitted to NITC. So the next issue is I want to talk about here is the dynamic traffic signal control. And but before that, let's take a look at a very popular application of CAV. Is called speed harmonization. So the CAV speed harmonization can be operated on either freeway or local arterials. And on the arterials, so we have to design to the vehicle trajectories and corresponding signal timing plan to maximize throughput and driving comfort, or minimize energy consumption, or ensure the safety of the vehicles. And the core problem here is the trajectory planning plus the scheduling. So let's take a look at those animations to show the benefit of the speed harmonization. So this first animation shows without the speed harmonization, we have the traffic get into the intersection, then we can observe a lot of stop and go condition because of the red light, and we can also see the shock wave caused by the red signals. And then if we can properly control the CAVs, and then if we can slow down the speed of the CAV, then we can smooth the traffic pattern and then allow all the vehicles to get into the intersection during the green light durations. So then we can remove the impact of the shock wave. We can reduce the number of stops and reduce the delays. But there's some argument on this issue here. You can see even though we can, so this would be the ideal condition, even though we can slow down the traffic. But imagine in practice, if you are the driver and you're following the one CAV on the street, and suddenly that vehicle slow down, and even though there's no traffic in front of that vehicle, then you may be pissed off, and then you decide to make lane changing to pass that CAV. So in practice, we can imagine without the control of the traffic signal, if you only place the control on the vehicle trajectory, you may even cause more and more lane changing behaviors, and also at the same time you may increase the crash risk on the street. So having that idea, in this project, we aims to develop a dynamic traffic signal control system, so at both intersection level and corridor level. At the intersection level, we aims to optimize the signal timing plan, including the phase plan and the signal timing and the cycle length in response to the real-time information. So that would be basically one typical adaptive signal control system. And then at the corridor level, we aims to optimize the offset in real time and try to provide signal progressions. And to evaluate the models we developed here, we use the vSim simulation network to look at the corresponding network performance, such as the delay and number of stops at those intersections. Firstly, let's take a look at the signal timing control at the intersection level. So as we know, the input information of vehicle arrival and departure pattern at the intersection are very crucial to the signal control, especially for the adaptive signal control. And traditionally, we're using the traffic sensors at intersections to detect the turning flow at each intersection. But considering the installation and maintenance costs could be relatively high to support those kind of functions, and in this study, we're trying to look at the possibility of only using a connected vehicle trajectory as the input to control the traffic signals. So here, in order to get the vehicle arrival pattern and also along with the Q length at each intersection, we want to look at the very important parameter that is called the market penetration rate, NPR, which is defined as a ratio of the number of CAVs to the number of traffic traveling through the network over a certain time period. And so when the market penetration rate is relatively low, let's say 5% or 7%, we aims to calculate that parameter, NPR parameter, based on all the vehicles on the network. But if we have a relatively high NPR, we can calculate the NPR for different approaches of intersections. So that would be depends on the level of the NPR in practice. And if we know the Q length with a unit of number of feet, we can also calculate the number of vehicles in the queue by dividing the Q length by the headway between vehicles. So that would be the logic that we're going to that will be adopted in this study. And then if we want to convert the CAV information into the number of vehicles and also number of queuing vehicles in practice, we are considering different cases here. So for the case one, we imagine there's more than one CV in the queue. So for example, in this case, we have 3 CVs in the traffic stream, in the traffic queue. Then we divide this entire queue length into 3 different parts. So the first part is the distance from this CAV to the stop line. The second distance is from the last CAV to the stop line, and then the last part is the distance from the last human-driven vehicle HV to the last CAV. So then we can, based on the headway and the trajectory of the CAVs, to calculate the different units here, and then we can estimate the corresponding Q length. And the second case is we only have one CAVs in the queue, so then we only consider 2 different distances here. The one is from the CAV to the stop line. The other one is from the last HV to the last CAV. So then if we can estimate these 2 lengths, then we can get corresponding Q lengths here, right? And there's the last case is we have no CAV or CV in the queue. So then we don't have any information for the estimation. In that case, we're gonna go ahead to adopt the information from the previous signal cycles for implementation here. So that would be the 3 different cases we consider in this study. So with those information, then we can estimate the vehicle arrivals and also the Q length at each intersection from each approach. So then we come out this real-time optimization model, which aims to minimize the travel delay at the intersections. And then we have a bunch of constraints to either calculate the intersection delay, estimate the Q length, get the vehicle arrival rate, saturation flow rate, and also along with some timing plan constraints. So this optimization model can be definitely solved by some offline technique like the linear programming or integer programming. But remember, this is this is adaptive signal control, so we have to get results in a very short time period. Let's say less than 1 second. So in that case, we implement the real-time solution algorithm, which is called dynamic programming. So the dynamic programming includes some basic features like the stage, state variables, decision variable, and value functions. And the logic here is we trying to find a path to connect different stage, and then we get the ultimate solution to connect different stage during different period. Then we can get the solution in a relative short time period. And in this algorithm, the stage is defined as the discrete time step. So we consider each stage as 1 second, and state variable is the total allocated time to each phase, and the decision variable is the green time allocated to each phase, and the value function is a total delay. So with this dynamic programming algorithm, we can solve the model within 1 second. Then we can implement that in real time. And so after the introduction of the intersection level control, let's take a look at the arterial level control. So at the arterial level, we will be more interested in the signal coordinations. And first, let's take a look at the concept of the traditional two-way signal progression. So imagine we have 4 intersections here. We have inbound direction and outbound direction. If we can properly design the signal progression plan, then we can provide a green band along these 2 directions. Then within the green band, vehicles can pass the intersection without any interruption of the red signals. So this is a traditional two-way signal progression, and I believe most of you are quite familiar with this concept. But imagine in practice, the major traffic flow may not traveling along these 2 through paths in practice. And then we come out another new concept is called the multipath progression. So here let's briefly explain what is a multipath progression here. Again, let's imagine we have 4 intersections, and if we have the one major path, that means we have a lot of traffic are traveling along this path in practice. So then if we can properly design the signal coordination plan, we can provide a green band along this path. And then at the same time, if we have another path, instead of to be a through path, we may have some turning actions along this path. So if we can properly design the signal coordination, again, we can still provide the green band along this path. So similarly, if we have another path along a different direction, still involves some turning action, we can also provide the green band. And then for the next one, we can also provide the green band. And then this is a summary of the green band for along different paths here. And so this is what we call the multipath progression. So we, instead of just provide the progression along the 2 through directions, we look at those popular or congested paths along the arterial, and we aims to provide the progression along different path flows. And so in this study, because of the we are developing the signal control system based on the CV trajectories. So then with the CV trajectory, we can definitely accumulate the CV trajectory, then to look at the most popular paths at along the arterial. So then we can identify this kind of multiple critical paths along the arterial. Then we can try to design the signal coordination plan to accommodate the traffic along those paths. So we have published a bunch of models to design the multipath progression about 4 to 5 years ago, but that is an offline model which requires maybe 10 to 20 seconds to solve the model to get the results. But in this case, we're designing the real-time signal control system, so we cannot use the offline model. So we update the model to a real-time version, and in this case, instead of looking at the green band along the entire arterial, we would be interested to look at the band between two adjacent intersections. So then, if we can somehow maximize the green band along two adjacent intersections, then we can maximize the band along multiple intersections. But here, there's a critical issue is if we only look at the band between the sections, then those bands may not be connected with each other. So for example, we can see the discontinuity between these two bands. Then in this case, we cannot have the green band that can pass through the three intersections in this case. So this will be the potential issue here. And in this study, we beside those typical constraints to control the green band between the sections, we also come out this set of constraints to ensure the continuity of the green band for pass along multiple intersections. And again, this model can be solved by dynamic programming to ensure the application in real time. And in terms of the stage, that is the index of intersections, intersection number 1, number 2, and number 3, and so on and so forth. And for the state variables, we use the feasible new offset of each control period at each intersection as a state variable, and the value function is the total green bandwidth along each pair of adjacent intersections. And this is a summary of the solution algorithm, but I don't want to spend too much time to go over the details of here. And in summary, we are also using the dynamic programming to solve the model. Okay, so now let's take a look at the numerical examples that implement the both intersection level and arterial level traffic control. And we're conducting the case study on 4 intersections on the State Street in Salt Lake City of Utah. And this is the signal timing plan for these 4 intersections. And with the CV data from simulation, we have identified 6 different traffic paths along these 4 intersections, from path 1 to path 6. And this is a summary of the identified time-dependent critical paths over different time period. So for example, for the first hour, we have the critical paths to be from 1 to 5, and for the second hour, we have the path 1, 3, 4, 5, 6 as a critical path, right? So this is the information we got from the CV trajectory from the simulations. And based on that, we have implemented our model, and we also make the comparison with 2 different models. So here, the adaptive control system refers to the one that only use the traffic sensors to detect the flow and only place the intersection level control. And the dynamic progression control system refers to the one that we have the adaptive control along with the two-way signal progression. So then the proposed control system is the one that we have intersection level adaptive control along with the multipath progression. And here these 2 figures are used to show the time-dependent travel time along path 1 and path 3. So we can see that with the multipath progression control, we can significantly reduce the travel time along those paths. And these 2 tables shows the network performance in terms of the average delay and average number of stops for all the vehicles on the network. And so the first table shows the comparison between the proposed control system along with adaptive control system. And we also look at different market penetration rate here from 25% to 100%. So here you can see that with the increasing of the NPR, the performance can be increased in terms of reducing the delay and number of stops. And the second table shows the comparison between the proposed model and the dynamic progression control systems. We can also observe the the improvement. But here you can see even with 100% of NPR, the improvement of the delay will be around 7% to 10%, which is not very significant. But this is a network performance that for all the traffic on the street. And if we only look at the performance along those critical paths, so then you can see the reduce of the delay and the number of stops can go up to even 5%, 50% under the 100% NPR. Even though we only have 25% of NPR, we can reduce the delay along those critical paths by 30% in those cases, right? So in this case, we can see we can with the multipath progression, we can reduce a lot of the delay along those heavy flow paths in practice. Okay, so in the next part, I want to introduce another smart traffic signal control system here. And in terms of the background, in this system, we aims to improve both mobility and safety. So that will be the extension of the model we just introduced. And so for that model, we only aims to improve the mobility performance. But for this case, we also aim to improve the intersection safety. So at the intersections, we may observe two types of crashes. The first one is a single, the side angle crash, and second is a rear end crash. And the side angle crash can be prevented by using some dilemma zone protection systems, DZPS. But for the rear end crash, some people argue that we may use the AWS, advanced warning system, to prevent the rear end crash. But after many years of implementation, this solution is still questionable because we don't see too much crash reduction, even though we're using the AWS in practice. So in summary, the prevention of the rear end collision at the intersection is still an unsolved problem. And the traffic safety and mobility are usually implemented with different control devices. So for example, we're using one package to improve the safety, we're using another package to improve the mobility. So then you often compete for the limited available resources. You're compete for bar data, where they're compete for space to install the sensors. So here in this project, we aims to integrate the control devices for both operations and safeties, so as to concurrently achieve the effectiveness to these two regards in terms of improving safety and mobility at the same time with one single unit. And this is the architecture of the proposed system. So we have the traffic signal light here, and we have a RSU to collect the real-time CV information, and also we can use the RSU to send back the information back to the CVs along with the advisory speed. At the same time, because we also have a lot of human-driven vehicles, the HVs on the street, so we're using the dilemma zone detection sensor to detect the trajectory of the HVs in real time. And also we're trying to use the VSL, variable speed limit, to control the speed of HVs, right? So in this case, we have a one important assumption is when we are providing the advisory speed to the CVs, the CV will follow the advisory speed. But when we provide the advisory speed along with the variable speed limit to the HV, so there's a compliance rate issues here because some people may not follow your speed limit in practice. So those would be the basic assumption of the proposed system. And by the way, this system is also one extension of the system that has been implemented in Maryland. My PhD advisor, Dr. Chen, and they actually implement a very similar system in practice, but they don't have the RSU along with the CV advisory speed. And this is a system data flow. So we have the different data resources here. We have the microwave sensor that can detect the the arrival of the human-driven vehicles, we have the RSU to collect the CV data in real time, and we have a signal controller. So then, along with those sensors, we can get different type of data. We can have the HV location and speed, and we can have the CV trajectories, and then we can have the SPAD information, the signal phase and timing plan from the RSU. And then in terms of the control modules, we have 4 modules here: dilemma zone protection, queue evolution, estimation, real-time signal control, and real-end crash preventions. And in terms of these 4 modules, the first module is for safety purpose, and second module is for both safety and mobility purpose, and third module is for mobility improvement, and the last module is for safety purpose. And for the first module, dilemma zone protection, so here this module aims to predict the vehicle passing probability at intersections, then decide whether or not we should provide all red extensions to prevent those vehicles that pass intersection at the last second of the yellow time. And so this is a very typical dilemma zone protection system. The second module aims to estimate the queue length at each approach of each intersection. And as we mentioned, we're using 2 different sensors to collect the information. We're using the microwave sensor to get the location of the vehicles in real time. We're using the RSU to collect the trajectory of the CVs. But here, there's a difference between the data from different sensors. For the data we got from the microwave sensor, we can only get the location of the vehicle in real time, but we don't really know which lane of the vehicle are sitting in real time. So, for example, we know the vehicle is over here, but we don't know which lane the vehicle is on. But with the RSU, we can get the CV trajectories. Then in that case, we can get the exact location on which lane, and also the location of each CVs in practice. So in this case, we have 2 different data, and then we can implement the queue length estimation model we just introduced in the last study to estimate the queue length in real time. And again, we have three different cases here. Case 1, we have more than 1 CV. Case 2, we have only 1 CV, and case 3, we have no CVs in practice. And module 3 is also the implementation of the signal coordination and CV speed harmonization we just introduced before. And then in the module 4 is to prevent the rear-end crash. And here we have 3 different sub-modules. The sub-module 1 is to prevent the crash when the vehicle arriving with insufficient sight distance after the onset of green. And sub-module 2 is to implement it after the onset of red. And sub-module 3 is to implement when during the yellow and orange times. And we don't have enough time to go over details of different control modules, but we have a paper published on the TR, and if you will be interested on the details, please go ahead to look at this paper with more information. And here is the system control logic along with actions. So based on the signal status, if it is during the yellow and red time, we activate the safety related modules to either protect the dilemma zone or mitigate the rear-end crash with the aura extension and advisory speed for safe stop. And if that is during green duration, we activate the mobility function to promote the signal progression. And again, we're providing the advisory speed for progression. Also, we do the real-time signal coordinations. So this would be the logic that combine both safety and mobility functions together. And here, in terms of the numerical test, we conduct a study on 5 intersections on the CV corridor operated by UDOT. And we also evaluate the system performance with vision simulation. And here, in terms of scenario settings, we have some basic settings here. We assume 40% of the the regular or human-driven vehicles compliance rate to the variable speed limit. And we assume there are 10% of the connected vehicle or connected automated vehicles on the street. And in terms of the model evaluation, we evaluate different models for comparisons. We look at the pre-timed traffic control, and we look at the dilemma zone protection system. So which means we only have the safety modules only. Then along with the proposed system, which include both safety and mobility modules. And for the safety MOE, a measure of effectiveness, we look at the average number of vehicles trapped in the dilemma zone, average number of potential side angle crash, number of potential rear end crash, and also number of red light running per signal cycle. And for the mobility, we look at the number stop and vehicle delay at intersections. So this result shows the comparison between these three different systems in terms of different safety MOEs. So we can see that for the number of vehicles in the dilemma zone, because we have the signal progression, we can reduce that a little bit. But in terms of the number of potential side angle crashes, both dilemma zone protection system and the proposed system can reduce that rate significantly. And in terms of rear end crashes rate, only the proposed system can reduce that. And in terms of the average number of running red runnings, the proposed system can also reduce that a little bit. And for the mobility MOEs, there's some interesting result here. You can see with the dilemma zone protection, we can even increase the number of stops and the average delay at intersections because we're activating the ORAD extension in practice. But with the integration of the both safety and mobility function, we can at the same time we can improve the safety performance and also improve the mobility performance here. Okay, so let's spend maybe 1 to 2 minutes to have some more discussions on the role of governments, considering most audience are from the government agency. So I have some discussion with the UDOT folks, and the common question is they're more interested in connected vehicle technology, but in terms of AV technology, their question is why we care about the AV related projects, because we're not the government is not the AV company. They are not actually producing the AVs. So in terms of the roles of the government, well, the government can definitely choose to do nothing, to let the operation of AVs without connections. But as mentioned, the AV, the priority of AV is safety. So if we only have AV on the street and everyone is based on the reactive control, then we can even make our traffic condition worse. So this, if the government is not do nothing, and they can also definitely promote the CVs. So with the promotion of the CVs, there are definitely some opportunities along with the liabilities in practice. So here the opportunities is to demonstrate the benefits of CV over the AV alone, but at the same time we also have some potential liability of providing CV data. So for example, we're providing the SPAD information to the CVs, and the CV relies on the SPAD information to operate the vehicle automation function. But imagine what if your SPAD information is not reliable? So that can potentially cause the traffic crash in practice. So in that case, the liability goes to the government because you're providing inaccurate SPAD information to the CV automation functions, right? So there are some other interesting topic here. Currently, it's very expensive to get a CV. We have do some budget stuff for one project, and it costs about 400K to get a CV to do the field demonstration. But Karma, they kind of provide this kind of toy car to test with their Karma driving system, and it's called Karma 110. So they said the cost of this kind of small car is about $3,000 to $4,000. So which is quite affordable for most researcher and government to test the automated driving systems, and also they're promoting some Karma Cloud platform to support the CAV operations. And we're working on one of the projects to develop the CAV, the Karma speed harmonization algorithm for them. And finally, I want to acknowledge some agencies that sponsor the projects, and the research is mainly sponsored by NITC, and also we have some partial support from the FHWA and UDOT and the MPC at the same time. All right, that's it, and I'll be happy to answer any questions.
Thank you, Terry. Yes, please submit your questions in the questions box of the GoToWebinar console. Thanks a lot, Terry. So when you spoke with UDOT and I imagine the other stakeholders that funded this, and asking them about, the possible uses of it, was your proposed system, is there a cost involved?
So we have discussing the potential project with UDA since last March, and what we're proposing is to demonstrate some level 3 connected automated vehicles on the CV corridor in Salt Lake City. And so there are different costs here. The first cost is the infrastructure-based cost. So that belongs to the government agency. So the DOT have to install the DSRC-based RSU, the roadside unit, to collect and also provide information back to the CAV. And the second cost is the traffic control cost. So they invest a lot of money to connect the roadside unit with the fiber cable to the traffic operation center. And so that will belongs to the government side cost. In terms of the user side cost, we got a quote from one company. It's called Autonomous Stuff. So they gave us a quote for one single CAV is about 400K. So to the best of my knowledge, Autonomous Stuff is maybe one of the most popular company that provide the CAV product that allows you to provide real-time control. So there are some other like AV, like Tesla or Google Car, but they don't open the platform for you to do the real-time control. But the car provided by Autonomous Stuff, they have a AutoWare platform that allows you to do your own programming, to do your own control. But the cost is relatively high. It's about 400K. And also, even with that car, we have to invest a lot of money to develop our own control algorithms, because they only provide you the platform to connect the sensor with along with the so there are the three components. The first component is a sensor, like LiDAR sensor, camera sensor, radar sensor, and then the second component is the driving software or platform. They develop the platform based on AutoWell, and then the third component is the CAN bus that allows you to control the gas panel and the wheel and also the brake. And so what they did is they built up the connection between the sensor and AutoWell, and also another connection from the AutoWell to the CAN bus. But in terms of how you're gonna control the vehicle, you still have to develop your own algorithm. So there will be definitely another cost to develop those software and programs to control the AutoWell, the automated driving systems.
Great. Yeah, there's a question maybe about sort of what comparing where UDOT is and with maybe other places. And so one person in our audience is asking what would be the greatest challenge of this system in a developing country like India. But I can also imagine that in different states and cities there are different challenges. Is that something that you can speak to?
Yeah, sure. So there are definitely both challenges in developed country and developing countries. So in terms of developing countries, my understanding is the how you can convince people to get those smart cars. Because imagine you have either connected vehicle or connected automated vehicles, you have add a lot of additional cost to the cars. So how you can convince people to get a more expensive car just because of those additional sensors on board. And so, in summary, for the developing countries, I feel like the most challenge is about the market penetration rate. So if you have a low market penetration rate, then the benefit of the CV-based system will be very limited. And in the developed countries like the US, currently we have seen a very critical issue is about the SPAD information, the signal phase and timing information. So the RSU, the DSRC-based RSU are broadcasting the SPAD information to the traffic. But here the issue is, in the US, most intersections are operated with actuated signal control system. So in that case, the signal timing plan are actually changing over time. And even the signal controller has no idea about when they're gonna cut off the green light for this approach. So then, in most cases, based on my understanding, a lot of states they just broadcast the base plan of the SPAD information. So then you can imagine the SPAD information is not accurate enough for the CVs to plan their trajectories, because maybe the SPAD tells you there will be another 10 seconds remaining for this green light, but after you get to the intersection, then you only have 80 seconds left because they cut off the signal earlier based on the sensor data. So in that case, I know there's a bunch of company and also universities that have been working on an issue is called SPAD prediction. So how you can predict the SPAD information and then provide that information to the CV. And another challenge I've been observing for both developing and developed country is the cybersecurity. So because currently the CV communication technology is very vulnerable. I have some discussion with my colleague, which is also the co-PI of this project, and he's from the ECE department, and he said it's very easily to attack the current CV communication system, because there's no cybersecurity or protection system has been implemented. So we can imagine if someone hack your communication channel and then provide the spoofed information to the vehicle, then that can cause a lot of traffic crashes. For example, even though the current signal light is green, then it tells you it's red, or current signal light is red, then it tells you it's green. And if the vehicle based on that spoofed information, then we can observe we can expect a lot of potential crashes.
Okay, so I think you touched on it, but maybe just clarify or explain a little bit more about small improvements in delay with 25% and 50% market penetration rate. If you have any thoughts on how to further increase reductions in delay without full market penetration.
Let me go back to the, okay, so here. Yeah, so definitely with the increasing of the NPR, we can see the improvement of the reduction of delay and number of stops. But also at the same time, we can imagine in the near future, we cannot expect 100% of NPR in practice, and most of the time that would be relatively low market penetration rate. So in terms of how to improve the performance of the system under the low NPR, my imagination would be to improve so that would be like two aspects. The first one is to to provide some education to the drivers. So back to the animation I'm showing here. Let me go back to, oops. Okay, over here. So in this case, even though we know if we can properly control the trajectory of the CEV, that can allow everyone to get into the intersection during the green light. But as I just mentioned, in practice, if you are the driver that follows the CEV in practice, you will be pissed off because you realize, you find out the vehicle slow down for no reason, and then you may decide to make lane changing and instead of following that vehicle in the traffic stream. And so I think the first aspect will be provide education to human drivers to allow them why the CEV is slowing down, and that is for the benefit of improving the traffic condition. And second one is definitely associated with that, that is to provide more advanced vehicle level control, because what you can do along from the traffic control aspect is limited, especially under the low NPR condition. So the second solution could be provide better vehicle level control to accommodate to try to provide better accommodation of the trajectory of operation based on the current traffic signal plan.
Great. Is there like a, you know, for the low NPR, is there an absolute like low NPR that would still work with the CV data on arterials?
So in another study, we have been testing some relatively low NPR, like a 3% or 5%. But in that case, if we still want to operate the real-time control system, you cannot only use the CV data as input. So in that case, we have to integrate the data from both roadside traffic sensors and the connected vehicles. So that would be the condition under the relatively low NPR.
Great. All right, it is after 11. I want to thank you so much, Dr. Yang, for presenting today. We can try to answer some of these unanswered questions that we received from the audience. And we will get an email out to you with links to the recording and the slides. We have a Friday transportation seminar coming up this Friday. It starts at 11:30 a.m. Pacific time. It's on how Portland is managing speeds for safety. And then we have another webinar next Tuesday morning at 10 a.m. So please join us again. Thank you.
Thank you. Bye.